Hey everyone, I'm Baba Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will talk about AVL trees. We shall begin our session by what is an AVL trees. Then we will discuss various rotations we can perform to balance AVL trees. Then we will discuss the complexity of AVL trees. After that, we will try various operations on them like insertion, deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn's YouTube channel. So let's get started with introduction to AVL trees. An AVL tree is a height balanced binary search tree. For each node, we have to make sure that the height of the left subtree and the right subtree can differ by at most 1. We can calculate this balance factor by subtracting the height of the left subtree from the height of the right subtree. Now let's discuss various rotations we can perform on AVL trees. First up, LL rotation. Next, RR rotations. Next, LR rotation. At last, RL rotation. Let's discuss them in detail. First up, LL rotation. It is a clockwise rotation when a node is inserted on the left subtree of the left subtree of a node. Then we apply this rotation to balance the tree. It is applied on the node below the balance factor 2 node. That is, we will apply right rotation on the green node. Next, RR rotation. When a node is inserted into a right subtree of the right subtree of a node, then we perform RR rotation. It is an anti-clockwise rotation which is applied on the node below a node having balance factor -2. That is, we will apply it on the green node. Next up, LR rotation. When a node is inserted into right subtree of the left subtree of a node, then we perform LR rotation. It is a combination of RR and LL rotation. First, we will apply RR rotation on green and yellow node. After this, red node is still unbalanced, so we will perform LL rotation on the yellow node. Finally, RL rotation. When a node is inserted into the left subtree of a right subtree of a node, then we perform RL rotation. It is a combination of LL and RR rotation. First, we will apply LL rotation on green and yellow nodes. After this, the red node is still unbalanced, so we will perform RR rotation on the yellow node. Now, let's discuss complexity of AVL trees. First up, space complexity is a big O of n. Next up, AVL tree offers a complexity of big O of log n for searching. Next up, AVL trees offer a complexity of big O of log n for insertion. Finally, AVL tree offers a complexity of big O of log n for deletion. We have now introduced an AVL tree and rotations on it. Now, let's discuss some of the operations we can perform on AVL trees. First up, insertion and deletion. Let's discuss them in detail. First up, insertion. We will insert a node following binary search tree rules. Then we will check if the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will create its member as public. Int key node star left node star right int height. Now let's write a function to get maximum of two integers. So int max int a comma int b. Now let's declare a utility function to get maximum of two integers. So int max a comma int b. Now let's write a function to get the height of the tree. Int height node star n. Now if n is null, then we will return 0. Else we will return n calls height. Now let's write that function to get maximum of two integers. Int max int a comma int b. We will return if a is greater than b, then we will return a, else we will return b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. Node star node equals to new node. So node key will be equals to key node left will be equals to left. Node left will be equals to null and node right will be equals to null and node height will be equals to 1. And return node. Here we have kept height as 1 because at the new node is initially added at leaf. So by default it will always be at 1. Now let's write a utility function to right rotate subtree rooted with y. Node star right node star y. Now node star x is equals to y's left and node star e2 is equals to x right. Now we will perform rotation. So x right will become y and y's left will become t2. Now we will update the heights. So y height is equals to max of height of y left comma height of y right plus 1. Now x height equals to maximum of height x left comma height of x right plus 1. Now return x. Now let's write a utility function to left rotate subtree rooted with x. So node star left rotate node star x node star y will be equals to x's right and node star t2 will be equals to x's sorry y's. Now we will perform rotation. So y left will be equals to x and x right will be equals to t2. Now let's update height. So x height is equals to maximum of height of x's left comma height of x's right and y's height equals to maximum of height of y's left comma height of y's right. Return y. Now let's write a function to get balance factor of node n. So int get balance argument as node pointer n. If n is equals to null, then we will return 0. Otherwise, we will return height of n's left minus height of n's right. Now let's write a recursive function to insert a key in the subtree rooted with node and returns the new root of the subtree. So node star insert node star node comma int key. Now we will perform the normal BST insertion. So if node is equals to null, then we will return new node key. Now if this key is less than node's key, then node left will equals to insert node left comma key. Or else we will insert that in the right. Node right is equals to insert node right comma key. Now we will return node. This if else will make sure that we will reach to the leaf node and then we will insert the key. Now we will update the height of this ancestor node. So node height is equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor for this ancestor node to check whether this node became unbalanced. So int balance is equals to get balance Now if this node becomes unbalanced, then there are 4 cases. So if balance is greater than 1 and key is less than node left key, then we will return right rotate node. This if statement for the left case, so or LL case. Now let's write it for the right case or RR case. So if balance is less than -1 and E is greater than node right key, then we will return left rotate node. Now write for the left right case or LR case. So if balance is greater than 1 and key is greater than node left key, then node left is equals to left rotate node left. Now return right rotate. Now let's write the right left case or RL case. So if balance is less than -1 and key is less than node to the right key, then node right will be equals to right rotate node to the right, and we will return left rotate. Now we will return this node. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root. So now if root is not null, then cout root key, and now pre-order root. And pre-order. Now let's write the code for the main block. We will start with an empty tree. Node star root is equals to null. Now we will try to construct tree. So root is equals to insert root comma 10. Now root is equals to insert root comma 5. Root is equals to insert root comma 2. Root is equals to insert root comma 3. Root is equals to insert root comma 7, and root is equals to insert comma 9. Now let's try to print this tree. So cout AVL tree is equals to tree in pre-order pre-order root. Let's execute this. As you can see, we have successfully created our first AVL tree. Let's get back to slides. At last, deletion. We will delete a node following a binary search tree rules. Then we will check if all the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will define its members as public int key node star left node star right int height Now let's write a utility function to get height of the tree. So int height node star n. If n is equals to null, then in that case we will return 0. Otherwise we will return n's height. Now let's write a utility function to get maximum of two integers. Int max int a comma int b. So we will return if a is greater than b, then a, else b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. So node star new node is equals to new node parenthesis. Now new node will get key as key. New node left is equals to null and new node right is equals to null and new node's height is equals to 1 because new node is initially added as leaf. That's why it is always be given as 1. Now we will return this node. Return node. Now let's write a utility function to right rotate a subtree rooted with y. So node star right rotate node star y node star x is equals to y left node star t2 is equals to x right. Now we will perform rotation. So x right is equals to y left is equals to t2. Now we will update heights. So y height equals to maximum of height of y's left comma height of y's right plus 1 and x height is equals to maximum of height of x's left comma x's right plus 1. Now we will return this new root. So return x. Now we will write node star left rotate node star x node star y will be equals to axis right and node star t2 will be equals to y's left. Now we will perform rotation. So y left equals to x and x right is equals to t2. Now we will update these heights. So x height is equals to maximum of height of x left comma height of x right plus 1 and y's height is equals to max of height of y's left comma height of y's right plus 1. Now we will return this y. Now we will write a function to get balance factor of node n. So int get balance node star n. So if n is equals to null, then we will return 0. Otherwise we will return height of n's left minus height of n's right. Now let's write a function to insert a node. So node star insert node star node comma int key. Now we will perform normal BST rotation. So if node is equals to null, then we will return new node key. So now if key is less than node key, then node left will be equals to insert node left comma key. Now if key is greater than node key, then node right is equals to insert node right comma key. Else we will return node because equal keys are not allowed. Now we will update the height of the ancestor node. So node height equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor of this ancestor node to check whether this node becomes unbalanced. So if int balance equals to get balance of this node. Now if this node becomes unbalanced, then there are four cases that could be possible. First up, LL case. So if balance is greater than 1 and key is less than node left key. Return right rotate node. Now let's write right case. So if balance is less than -1 and key is greater than node right key, then we will return left rotate node. Now let's write left right case. So if balance is greater than 1 and key is greater than node left key, then node left will be equals to left rotate node and we will return right rotate node. Now let's write the case for right left case. If balance is less than -1 and key is less than node right. So node right is equals to right rotate node right. Now we will return left rotate node. Now let's return the unchanged node pointer. So return node. Now let's write a function to find minimum value node. So node star min value node. Node star node. So node star current equals to node. So while current left is not equals to null, current is equals to current at left. Now we will return current. Now we will write a recursive function to delete a node with the given key from subtree with the given root. So node star delete node. Its arguments are node pointer root, comma, int key. For starters, we will perform standard BST delete. So if root is equals to null, then we will return root. Now, if the key to be deleted is smaller than the root key, then it lies in the left subtree. So, if key is less than root key, then root left will be equals to delete node root to the left, comma, key. Now, if key to be deleted is greater than the root key, then it lies in the right subtree. So, else if key is greater than root key, then root right equals to delete node root right comma key. Now if the key is same as the root key, then this is the node to be deleted. So else if root left equals to null or root to the right is equals to null, then node star temp is equals to root left now if temp is equals to null, then temp will be equals to root and root will equals to null, else root will be equals to star temp and free temp. Else node star temp is equals to min value node root right. Now we will copy the in order successors data to this node. So root key is equals to temp key. Now we will delete this in order successor. So root right is equals to delete node root comma temp key. Now if root is equals to null, Then we will return root. Now we will update the height of the current node. So root height is equals to 1 plus max of height of roots left, comma, height of comma height of root right. Now we will get the balance factor of this node. So int balance is equals to get balance root. If this node becomes unbalanced, then there are four cases. First up, LL case. So if balance is greater than 1 and get balance of roots left is greater than equals to 0, then we will return right rotate. Now if balance is greater than 1 and get balance of root left less than 0, then root left will equals to left rotate root left. Now we will return right rotate root. Now let's write right case. So if balance less than -1 and get balance is less than equals to 0, then we will return left rotate now we will write right left case. So if balance is less than -1 and get balance of root right is greater than 0, then root right is equals to right rotate of root right. Now we will return left rotate and we will return this root. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root. So if root not equals to null, then cout root e a pre-order root left and pre-order root right. Now let's write a code for the main block. We will start with an empty tree. So node root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 10 root is equals to insert root comma 9 root is equals to insert root comma 7 root is equals to insert root comma 5 root is equals to insert root comma 3. Now let's try and print this of AVL tree. So cout created AVL pre-order pre-order now we will delete a node. So root is equals to delete node root comma 10 Now let's again try and print this. So cout modified AVL tree pre-order after deletion of 10. Layout handle pre-order root. Repeat. Now let's execute this. As you can see, our deletion function is working perfectly. Now let's get back to our slides. At last, let's sum up what we have learned from this session. First up, AVL trees is a self-balancing binary search tree. Next, every node must have a balance factor of either -1, 0 or 1. Next, after every rotation, we must verify if each node is balanced or not. Finally, AVL trees offers fast insertion and deletion operations. And this was all for today's session. Hope you guys found it informative and helpful. If you liked this session, then like, share and subscribe. If you have any questions, then you can drop them in the comment section below. Thanks for watching and stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.